In this tutorial, we will learn the structure of LMGC90 script, writing both script and running, and we will also visualize our data in ParaView. Here is the mechanism of LMGC90 simulation. For running LMGC90 simulation, we need to script two files. One is known as generation script and another is known as simulation script. Generation script will generate input file like .dat and .ini files which could be read by another script which we can call simulation script, and that will actually run simulation and which will generate some data like display, outbox, postpro and other output files. And output files and output can be used to restart the simulation if you want to restart. So here is some steps to write input files. First of all, we have to import modules, and then we will define some variables, and then we will define some containers, and we will define interaction, and in the last we will write output and postpro files. Containers are very important because they contains many information. The main geometrical part is avatars. Avatars are which we see in visual, and these are geometrical objects like wall avatar, particle avatar, floor avatar, which we can see. So avatars are also a container which contain wall, particle, floor, and we can define these avatars with material, model and interaction. So we have to define some container. Here is parts of avatar. Avatar consists of many parts like bulk and contactor and dimension. Bulk has materials. There are many materials like rigid, elastic, viscoelastic, elastic, plastic, thermoelastic and many. Similarly, we have many models like mechanical model, thermo model, porous model and multiphysics. And also there are many contactor like sphere, polygon, disk. Avatar also consists of nodes and group. Group are just a list of like list of bulk, list of nodes, list of contactor. The examples of node are like coordinate, DOF, degree of freedom, and numbers. So DOF may take value or some other driven data. So this is the mind map of avatars. So let us start writing script. So in this first part we will generate some output file. So we will write generation script. Let us write in Python. So these are some basic parts of writing generation script. So number one, we have to import modules, and then we want to define some variables. Here we will define some variables, and we will define containers. Then we will define interaction between particles and wall, and in the last we will write output. So main part of importing module is Pi LMGC90. You can see here I have written a script. Let me define. This is first importing module, defining variable, defining containers, writing outputs, and visualizing, and this is the end of script. We want to import this module. We will also define seed to generate random particles in a region. After that, we will define variables like friction between particles and wall. PP stands for particle-particle friction. Let us suppose we have two particles. There is a friction between two particles, and also friction between particle and wall. We will also define the size of particles. In this example, I will define a range of particles from minimum 0.5 to the maximum 2. We also want to define a simulation region in which we will deposit these particles, length Lx and Ly. And then I will define a region for particle generation. So this region will be smaller than the actual simulation region. And then I will define the number of particles which I want to insert. The dimension of my simulation will be 2D. After that, I will define containers. So first I will define orator containers like this. Body is equal to orator. This is empty now. And I will also define a material container. And visibility table container. This class define object to store the C table used by contact detection. And I will define contact behavior container, interaction model with its parameter. Now I will define material. For example, the name of material is teeter, and I can define like this. And another material will be plex for particles. Then I will add these two material into a container. Then I will define a model. So here I will use a mechanical rigid model. You can check the option of this material and model. Let us check what are the options. So you see that these are the options for bulk behavior like rigid, thermorigid, discrete. Here I have used rigid. You can choose any material type from these options. So let us see the other options of this material type rigid. Type rigid here. This will show only one option, density. So we have to put density here. You can also see the options of other material type like elastic. So elastic carries many options like elas, young, new, and density, and many. Let's see about the viscoelastic. These are options for viscoelastic material type. Similarly, we can also see the option for model. Just we have to write here model options. There are 4 physics model like thermo, mechanical, porous, and multiphysics. You can also see other options of any of this physics model like mechanical. These are all options of model mechanical. After that, you have to define orator definition. So first I will generate particles, and then I will deposit these particles in this particle region box px, py. So here is ready. After that, I will generate these orators. So first I will generate particle orator like this. I will define a body on which I will put all these particles with these options. I will add the model, material type, which I have already defined here, and also I will define the color for the particles. This color can be used and for other commands like defining interaction. So this is the reference. We can refer these particles later on. And then we can add these particles into a orator container which we have defined earlier like bodies. After that, I will define wall orators. There are 4 walls: down, up, left, right. We can define wall by this command from axis 1 to axis 2 and this option, and I also want to define the model and the material of this wall and also color. So I will define 4 walls and I will add these walls into body orator. We have a particle and 4 bodies which we have added to the orator container. We will also rotate these 2 walls left and right so that they can make a complete box. After that, I will define some boundary condition on the orators, for example on the walls. So I want to apply 0 velocity to all walls. Then we will define interaction between particle and particles and wall. So we can define by these options. We will use a friction we already had defined in the variable parts, friction between particle and friction between particle wall. So we will use here PP means particle, and we will add these interaction to the container. After that, we will define visibility table declaration between particle of type disk blue and disk blue, because we have only one type of color. And we will add these to the container SVS, and also we will define these tables for particle and wall and add to the container. Finally, I will write files. First we have to create a directory, dat box, and then write these statements to write files output. These input files can be used for next script to run simulation. So we will add these all texts, SVCs, velocity, location, everything we will write out. And we also want to visualize our operators, so we will write here. This is the end of script. So let us see our operator and run this script. Go to terminal, type here Python and write the name of script. So it will generate some file and this figure. Let us move our particles on the top, body.translate on the y-axis 40 and run again. You see now our particles are on the top. Let us write second part, simulation script. We will create another Python script. Let me write the name of script, compute. Open this script. First of all, we will import some module. Here we will import ChaiPy module for simulation. In the previous script, we have imported pre module. After that, initializing, checking and creating directory. Then defining variables, then model reading, and computation and simulation part goes here. This is the end of the script. I have written this script, so you can see how can we define this script. How can we write this script? We have to define variables time step, number of steps to be run for simulation, solver definition. Here we will use LMGC solver and their parameters. Module reading and computation. These are codes for module reading. These are codes for writing output and computation. And simulation part goes here. And in the end we will write some output. Let us run this script, compute.py. So it will run. So we have to wait until it finished. It will generate many files for ParaView and some outputs. Let us see. Let us visualize in ParaView. Now you can see the output of our simulation. Particles are falling at the bottom.